So we just got a couple caused on that beam. Call the left one A and the right one B for the reactions. Just find them. Now, the first thing you always do on these is make a free body diagram out of them, right? So even if you're not quite sure how to proceed, get that, start with that. And you know, when you're doing that, don't use tunnel vision. You got a pin joint there, and you got a roller. I mean, don't need any more other than that. Pin joint, it's two reactions, a roller against one, it's going to the surface. Okay, so that's the first step. Now what's the next step? And let's see. What are your choices for what to do with this? Yeah, write up some equations. That's a good idea. You sound like the boss. Okay, guys, go out and write some equations. Let's go. All right. All right, there we go. Yeah. Okay. Now, I guess sometimes, you know, if you're not quite sure what to do, we tend to just kind of look at things. But I think we might use our time more constructively if that's what we're up to, because there's the three choices for equations. It's got to be one of those three, right? Okay. So, which one do you think? You want one unknown, right? So what you gonna do? Okay, what's the equation that, okay, so sum of fx, yeah, you could do that. Okay, sum of fx, it's a good way to start, give you something to do while you're thinking about things. Rex is 0, right? We're done? Okay. That's good. Okay, now we're down to two equations. Now, how many unknowns do you got with sum of fy? Yeah, you get too many, don't you? So which one are you supposed you're going to do? Yeah, you got to do a moment equation, okay? And do one that'll get you down to one unknown. I'm telling you this, I'm kind of saying this to you because I remember once I had a dynamics test question and I had no idea what to do. And there was this collar with springs and rollers and it was just all over the place. And I just kind of looked at it and my eyes got wide and I kind of wrote F equals MA over on the side, kind of real small. I turned the page, I just didn't know what to do. But see, that's the wrong approach, right? Because you can see, if you just get a free body diagram, man, teachers love free body diagrams. Just give them that, if nothing else, they'll get you a couple points for it, okay? Okay, and also there's discrete steps to this stuff, all right? It isn't like it's wide open. You know, this isn't nuclear physics or something, it's just wide open. There's discrete steps. Draw a free body diagram and then use an equation. And there's only 3 equations to use, so pick one and try and use it, you know, as opposed to just kind of staring off into space sometimes.
So when you say the sum of the moment is 0,
yeah.
you're just saying it's at equilibrium there?
Yeah, right. Now you got to pick moments to take moments. You point to take moments about.
Yeah.
But okay, yeah. Why are you picking A?
Because because that way, we only need to worry about 2 moments.
Yeah.
So
Yeah, right.
Because the moment that A itself is producing, it's going to have moment arms.
Yeah, if you take moments at about A, you're going to eliminate REY and REX from the equation. They're gone because they go right through A. They don't cause a moment about A. Okay, so see, so now you got something to work with, eh? So you can always write that down. Now fill it in. And just take a minute and fill it in. And regardless of whether you know what you're doing or not, just fill it in. All right, so the idea here is there's discrete steps. There's not infinite possibilities. There's discrete steps you use when you solve out these problems. Apply the steps. And maybe you get something wrong applying the steps, but at least apply the proper steps. There's certain ways you solve these things, especially in statics. It's not very wide open. There's definite methods you use. So 1.2 RB, right? You all good with that? Because that's the moment arm to RB. It's counterclockwise about A, right? Coming around that. Whoop, darn that thing. Okay. Now, what do you do with that 960 Newton meters? Okay, write it down. That's good. I like that. Do we put a sign on it?
Yeah.
Okay. What do we do with the 0.4 meters?
Doesn't matter because you can apply them.
Yeah, see,
a couple anywhere you
yeah, you can put a couple anywhere you want. A couple affects the object equally regardless of where it's placed. The other tip off on that is look at the units, Newton meters. That is a moment. If you start throwing another meter unit into there, either dividing or multiplying or whatever, it's going to screw up your units, okay? So that's all you got to do, see? And that'll get you, then you can solve for RB, okay? 1.2 RB is 960 Newton meters. Okay, so regardless of where that couple's applied, it affects the object equally. It doesn't matter. So that the dimensions on that are a little bit of a red herring. Okay, they're not really needed. Okay, so RB is what is that 800? I think.
Yeah.
1.2. Okay, 800 newtons. Which way does it act?
Up.
Yeah. I assumed up. I got a counterclockwise moment, so that was a positive 1.2 RB. My answer is positive, so that means my assumption was correct. Okay, so that's 800. All right. So I got to find one more. What's the best way to find RAY?
That's going to be the sum of all the
What's that now?
It's going to be the sum of the two Y forces.
Yeah, right, yeah, okay. Sum of Fy equals 0. I got RAY. I've got plus 800, and then what do I do with the couple?
Nothing.
Yeah, nothing, because couples don't affect the forces, okay? Couples don't create a force. All couples do is twist. They're like pure moments, okay? The shaft coming out of a motor doesn't move something up or down or left, right. It just spins whatever it's attached to, okay? So no forces there, okay? So those couples they're funny, and that's why I put that in there, just so you know how to handle it, okay? So RAY, I assumed it's up, so I'm going to get a negative 800, so that means it's not up, it's down, okay? Okay.
So does that mean your free body diagram should be pointing the other way?
Okay, so we found out that RAY is down. Okay, and what's happening here is there's a counterbalancing couple in A and B to the couple that's applied. It's like the 960 is trying to spin that thing clockwise, so the reaction's got to go, no, I'm not going to let you do that. I'm going to spin back counterclockwise to prevent it. That's what's happening. Now, I normally don't adjust my free body diagram. Free body diagram is just what I assume going in. I clearly label my answers with which direction things are going. I like just a number and an arrow because it's completely unambiguous. So I don't tend to go back and fix my free body diagram.
Okay.
Leave it, and then just in your answers make it clear which way things go. Okay. All right. So we good with that? Okay. So that's how you handle a couple. And it's a little confusing. That's why I wanted to cover that, you know. But it's simpler than it ought to be, I guess, is how it seems to people. So on the left-hand equation there, I just subtract the couple because it's clockwise. I do not include a moment arm on that. Okay, the couple will affect that object with that torque regardless of where it's placed on the object. And the units are really, if nothing else, the units will tip you off to that. It's already a moment. You don't have to do anything to it. Just leave it in Newton meters. And then on the force equation there, the couple does not cause a force. It's just a pure twist. Okay. Oh, there we go. All right, so that's that one. Okay, so that's a start on equilibrium there with objects that are basically one-dimensional, beams and columns and stuff like that. Okay. So that's where I like to start. Now the next place to go with this is beams, objects that are two-dimensional, brackets and frames and things like that. So something like that, okay? So that's going to have a couple reactions at the wall that we'd have to account for. We might have an angled force on there. We could have all sorts of things going on. There on that bike rack there, we've got, you know, a two-dimensional object. So let's have a look at this one. All right, so we got a L-shaped bracket there with a roller on it and a pin joint. So make that into a free body diagram. Okay, so when you make something into a free body diagram, put the weight on it, you know, draw the boundary, look for contact forces, look for the reactions and what sort of supports they are. don't overthink it. Just look at those supports and put in forces that they generate to hold the thing in equilibrium. Remember to, if you got any things that aren't horizontal or vertical, label the angles, because you'll need those. Okay. So I got something like that. Two reactions at the pin joint, one at the roller. Okay, what you do with that force at the roller is draw it perpendicular to the ramp. And the general rule on that is to find the angle of the force, you take 90 minus the angle of the ramp. Okay. So what's going on there is we got a 60-degree angle for the ramp. We then have a force that's normal to the ramp, like so. So, and we know that's normal, so that's 90, that's 60. So what we're doing here, we're taking the full angles in a triangle, 180, we're taking that 90 off because we're dealing with a right angle, right triangle. So that gets you down to 90, and then you subtract the 60 and get to 30. That's what you're doing. So you don't really have to go through that every time. Just remember that the force angle is 90 minus the ramp angle, if the force is normal to the surface, okay, or the ramp. Okay. So that's where that 30 comes from. Okay, y'all okay with that? Any questions on that bit?
Is it always going to be normal?
Yeah, if that's smooth or a roller on there or whatever, right? Because you know that's the rule on that type of support. So yeah, I'm just kind of thinking about your question. I mean, pretty much every time I can't think of times when they're not. Okay.
As far as this goes.
Yeah. Okay. Yeah, there you go. Yeah. Okay. All right. Now, so on these free body diagrams, we want all the forces. We want dimensions too, which we've got. We got the dimensions on the bracket and the dimensions of that center of gravity. Notice the 20-pound weight goes at the center of gravity. But we got one little complication here, and that's that reaction is touching the roller, not the point B. Normally when you dimension these things, you go to the pins on them. That's normally how you dimension them. So we're going A down to that right angle, and then from the right angle over to the pin at B. But the force isn't on the pin, it's on the roller. And that's a circular roller. So now we got to figure some stuff out here. Where is that force on the roller exactly? Because that will affect our moment arms, see? So we're going to have to kind of get that worked out. And luckily, it's a pretty easy thing to do. Okay. And here's the deal. I didn't. Okay. All right, so what we've got there is we've got a tangent line to the circle. So the roller's a circle, and we've got a tangent line to a circle, okay? Because the ramp is tangent to the circle. That flat ramp is tangent to the circle. And then we've got a force that's at a right angle to a tangent line at the point of tangency. Well, it just so happens if you check with your math instructor, I'm sure they'll be able to tell you that that goes right through the center of the circle. If you've got a perpendicular to a tangent line at the point of tangency, it's pointed through the center of the circle. And I don't know how you prove that, but it's how it is, okay? So the deal is you don't have to worry about that. So the dimensions on the roller don't matter. What you do is you just take the force and project it. Remember, you can project forces anywhere along their line of action you want. So you can just put it right at the pin, right at B. which is a good thing, because that's normally how those things are dimensioned. They're dimensioned to the pins, you know. Okay, so we can just take that force on the roller and just apply it at the pin at B, and then we can use that 6-inch dimension when we do it, and the 8-inch dimension too. All right, so that's generally how you handle the rollers. Just apply the force at the pin in the center of the roller. Okay. All right, so now we've got to figure out how do we start approaching this thing, okay? Because, you know, we've got different equations we can use. You know, we got the force equation, sum of Fx is 0, sum of Fy is 0, and then we got moment equations. And the moment equations are flexible. You know, you can take moments about any point you want. So what I always want to do on these is kind of start with an equation that gets me one unknown. So sum of Fx is 0. How many x unknowns do I have? Yeah, it looks like 2. I've got Rex and Rb. Rb has an x component. And then I got Rey and Rb. So I don't want to start with a force equation, because I'm going to get into one equation with 2 unknowns and it'll just get a little messy. So I think I'm back to moment equations. So where could you take moments about so that you'll only have one unknown to deal with?
Pin.
Yeah, pin, which one? I think A, yeah. So I think if you do that, sum of MA equals 0, you'll have one unknown. You'll be able to find Rb. And then you can use force equations after that to solve for Rex and Rey. So that'd probably be the best strategy for this. Start with sum of MA equals 0. You'll just have one unknown. So that'd be the way to go, okay? You want to be thinking about this stuff, and it's real common if you got a pin joint to take a moment about a pin joint, because a pin joint always has 2 unknowns, 2 unknown reactions. And if that's the case, it'll only be one other unknown that you can solve for using statics in 2D. So you can solve for the third unknown by taking a moment about a pin joint. Okay? It's often the best way to start. All right.
And can you do it with one that has, or can you start with an equation that has 2 unknowns and just,
Sure.
I just substitute it?
You can. It's just messier.
Yeah.
But now, if you're going to use your calculator or something, you got a a multiple equation solver. You could do it that way. It wouldn't matter in that case. But if you're going to solve it by hand, it's a lot easier if you can find one with one unknown. But it doesn't make a difference. You know, it all works out. Okay. All right. Now, one thing I'll point out to you is the difference between the pin joint at A. That has 2 independent unknowns, Rex and Rey. They're independent of each other. They're not related to each other directly. Now, Rb has 1 unknown with 2 components. Okay, so those are different situations. The pin joint has 2 independent unknowns, Rex and Rey. But that roller at B has 1 unknown, Rb, which has 2 components, cosine 30 Rb and sine 30 Rb. So don't call this Rbx and Rby. It's quite misleading, and I've seen people do this before because they kind of forget that they're connected to each other. They're not independent unknowns. And I see people get into trouble when they start writing up equations and you write them up this way, because what Rbx is cosine 30 Rb. Okay, that's what it is, and what Rby is sine 30 Rb. Okay, so it's a little bit misleading to write them up as shown there. I don't think that's a real good idea. It kind of confuses things a little bit sometimes. Okay. All right, so we'll take a moment about A, is how we'll start this. So why don't you just take a minute and come up with an equation. I think you're going to have 3 terms in there. When you take moments about A. So sum of MA is 0 equals, and there'll be 3 terms with, distances and forces. And I'm not sure what the signs are, but, you'll have to figure those out. Oh no, 4 terms. My goodness, we've got a lot of terms in that thing, don't we? 4. I didn't notice that 40 pounds pushing on the thing. So remember, X forces, Y moment arms, Y forces, and X moment arms. That's how they combine. Watch the signs on this stuff. That's it, force out.
This is right here. Yeah, this is on. This one's on.
Doesn't say, I don't know what you're saying.
Well, it depends on what you're using the triangle for. Okay. Now, if you just want to find what the angle is, you can draw a triangle. Okay. Yeah, but you're right. I mean, the total force is the triangle.
Yeah, that looks right.
I don't know what the left one would be, what, like, so this one,
This is.
I would use this triangle here to do the vector. You can write this.
It's a moment, so maybe you're not, this is. This is the moment about it. So this is already happened at it, so I don't think we're gonna do that.
Yeah.
This would be times because, I don't know, like, usually the moment is like short distance, but it's like as we're song.
So then it's 5, and you also put cosine 30 degrees. So that makes
This is offset by
Oh, yeah, you can put down the
Simply to find out that 30-degree angle. So our look at 30 so.
Are you saying it's going 40 pounds straight?
No.
Yeah, I see that, but once again,
I had a specific case with that triangle, but I wouldn't break it back to just. It needs to be
It's a small block.
another, that's a
Or 3 maybe.
Did it come? What do you think of it's already out. 4-year-old I wish we had gotten this first one. Nothing special.
You all right with this? 73, 74 pounds. Trying to get out. Yeah, if you bust one sign or one moment arm, of course, that's throw everything off. It's gonna be it. Any questions on what I'm doing there? Everybody all right with that?
You're okay with a non-standard foot pounds?
Either just pound it.
As long as I stay consistent on moment arms, it's okay to use inches. There's no harm in it, but just stick with it, you know, through the whole problem.
Yeah.
Yeah.
You're saying that positive is to the right?
No, these are moment equations. So positive is counterclockwise and negative is clockwise. Right and left don't directly mean anything on these things.
That's 6 inches on the very end of that.
Yeah, it is 6 inches, which is that, that distance over from the corner to B. I think that's 6.
That is what's nice about it. Self-clean is the one.
You all okay with that? Any questions? Right, so just watch your signs carefully, you know, and all that. Okay, and then once you got that, you want to find the other two, REX, REY, and don't mess with moment equations on those, just do force equations, simpler, more direct, you know. You can just solve for them directly with force equation. Okay.
So even though you're doing the forces now, you're still thinking clockwise?
No, force sign conventions are up, down, left, right. So moment conventions are one thing, forces are basically another. I don't relate them together, if you know what I mean. And then I got a negative answer for REY. That means it isn't up, it's down. When you push that bracket on the ramp pushes it up. So REY has to push down to hold equilibrium. Still doing okay with that? You got any questions on it? Doing all right? Yeah, pretty much, yeah. If you want to find the total force on the pin, what are you going to do with that? Okay, the simple answer to that, just be square root of some of the squares. Now, it might depend a little bit on how that pin is attached with the roller and all that, but for what our purposes, we could just use square root of some of the squares. Okay. So 29.3 pounds. Okay. All right, so when you get into these two-dimensional problems, you know, you a little bit more strategy on these sometimes, and you get into more complicated moment equations, of course. The next one's a little trickier yet. That's on page 430. So we good on this one? We got just a couple minutes, so why don't we start looking at this next one? We're good? Okay. Okay, why don't you get that turned into a free body diagram real quick? So that's always step one in this class, pretty much. I mean, whenever we're doing force type stuff.
Is that a cable?
48, it's just a force of some type. I guess, you know, they're not really calling out exactly what causes it, but yeah, it's pulling on that angle there. 48. Okay. Don't have to worry about the weight of the bracket on this one. Okay, so there's a free body diagram, two forces at the pin joint and a force at the roller. And that's pretty much it, right?
Why don't you worry about the weight of the bracket?
Because it's not given, and so I'd assume that it's insignificant compared to the forces applied. All right. Now, how are you going to start this one? What's your first equation going to be on this, do you suppose? Yeah, a moment about A, okay. Why? Yeah. A's a pin joint, and so I want to find take a moment about that. I'll eliminate the two unknowns. I can solve for the third at C. That's the idea. All right, now, the one thing, and of course we don't have time today, but the one thing that we're going to do here is we are going to want to dimension things from A. So that's what we'll look at tomorrow is just this process. It's not nothing too fancy, but just be sure that you've got nice square dimensions to get from A to wherever those forces are at B and C. So you're going to want X and Y dimensions from A to B and X and Y dimensions from A to C. That's how you want to approach this. That way you'll be able to find those moments pretty readily. Because when you're doing moments, you combine X and Y forces with X and Y distances. The X and Y distances are the dimensions. So we want to get that figured out. So that's what we'll look at tomorrow. Why don't I give you just one of these, about 263. So 263, I guess we'll make that due Friday.